So Gaussian random variables, let's talk about those. The reason we want to talk about Gaussian random variables is that we are going to use them, well, one of the reasons is that we are going to use them a lot to generate the artificial data that we're going to be working with when evaluating and benchmarking various machine learning schemes. The reason that Gaussian random variables arise a lot in practice is because of the central limit theorem, right? So let me just informally state the central limit theorem. So basically it says that when we add up a lot of random variables, let me make it many random variables which are roughly independent. Again, I'm stating it very, very informally. Roughly independent. Then the sum looks Gaussian. And that's really the level at which I want to talk about it. It's pretty easy for anybody to look up the formal statement of the central limit theorem and various variations of it. But this is good enough to sort of motivate why we want to look at Gaussian random variables. So let's look at what the density of a Gaussian random variable looks like. That's a standard sort of bell-shaped curve. So let me draw a bell-shaped curve. And I'm going to draw some sort of arbitrary sort of axes here. This is the values that the random variable can take. And this is the density of the random variable. As it turns out, the Gaussian random variable's density has a peak at, let's call this number m. That m happens to be the mean, the median, and the mode of the Gaussian random variable. So basically, the maximum value of the density is at the mean. So the mean is also the mode, and the density is symmetric around the mean, and so the amount of probability to the left side of the mean and the right side of the mean are the same. So the mean is also the median, right? So that's what a Gaussian random variable looks like. If I look at the max here, the amount by which the speed at which the density decays away from the max depends on the variance. So let me just write down without further ado the form of the density. It's p of x, and I'm going to denote it by in this way: n of x given m and v squared. Or let me actually make it sigma squared. Sigma squared. So basically it's saying that this is a Gaussian random variable is often also called normal. So the n is for normal. A normal density with mean m and variance sigma squared. And let me write down the form of the density. It's exponentially decaying as this. So basically, I'm looking at the deviation away from the mean, x minus m, and squaring that. It's only the sign of the sign does not matter, only the size matters. And how fast it decays depends on how big the deviation is relative to sigma squared. And sigma squared is called the variance, and sigma is called the standard deviation, right? So these are just basics of Gaussian random variables. Let me write that down here. Sigma squared is the variance, and sigma is the standard deviation. So that's as far as the single Gaussian random variable goes. We often want to talk about multiple Gaussian random variables defined on the same probability space, which means we can talk about their joint distribution. So let's write that down. A Gaussian random vector, and that's bold X, but I'm going to here just write it as X with a bar below. And let's say it's it's d-dimensional, so it has got d components. Let's denote them by x1 through xd. And for now, we'll think of vectors, unless I specify otherwise, as column vectors. So I've written this as a row vector, so I'll just put a transpose there. Again, we can talk a lot about these, but we are just going to state the basic facts. A Gaussian random vector can be characterized by, just like the Gaussian random variable could be characterized by the mean and variance, it can be characterized by a mean vector, which is just the individual means of these guys, right? Basically, it's just expected value of x1 through expected value of xd. That's the mean vector, and the covariance matrix. C. So this is a mean vector is of course d cross 1, and the covariance matrix is a d cross d matrix whose I only need to specify its ijth entry for you, so I'm going to denote it like that. The ijth entry is the covariance of the ith random variable and the jth random variable. And so now we have to go back and define covariance. So basically you've got a d by d matrix filled up with these entries, and let me just define covariance. Covariance of, and I'm going to just generically define covariance. Covariance of two random variables u and v can be thought of as how u and v sort of co-vary around their means. So you get rid of the means and then look at the product, the expectation of their product. So you can see that you can, certain properties of covariance fall out immediately. Like if I add 10 to u and 20 to v, they would not change the covariance, because the 10 would become part of the expected value of u and it would get subtracted out, and the 20 would become part of the expected value of v and it gets subtracted out. So there's a bunch of properties of covariance that you can write out. It's insensitive to translation. If I scale u by 10, then the 10 just pulls out because it's there in u as well as e of u. So there are all these properties that we can dwell on, but we are not going to dwell on right now. So anyway, that's what the covariance is. And you can see that the variance is a special case. The variance of u is just its covariance with itself, right? So that's what the covariance is. So what does the density of a Gaussian random vector look like? And I'm going to write it in the same kind of notation as before. So it's n of x given, for parameters m and c, is exactly similar to what you had before. So you have a minus half, you subtract out the mean, and instead of dividing by the variance, you take the inverse of the covariance. That's a natural generalization. And instead of squaring x minus m, you're doing basically x minus m transpose c inverse x minus m, right? So this is what you have. And then instead of dividing by square root 2 pi sigma squared, you divide by 2 pi to the power of d over 2. So for dimension 1, it becomes 2 pi to the power of half, which you had before. And then instead of sigma squared to the power of half, you have this thing that I've written, which is the determinant of C to the power of half. So this is the determinant of C. Now, this density only exists if C is invertible, and I can write this C inverse term. C does not always necessarily have to be invertible. You can have jointly random Gaussian random variables whose joint density does not exist. But again, that's a nuance we don't need to go into for the purpose of this course. So the contours of a Gaussian random vector are elliptical, because what they correspond to, if you look at the Gaussian density out here, the density will be constant if x minus m transpose C inverse x minus m is a constant. So that is basically the equation of an ellipse, right? So that's where I'm sketching these. I've sketched these ellipses out there. They're centered around the mean, of course. So this is the mean. I've shown a two-dimensional density, which is all I can sketch, the contours of a two-dimensional density. So this is what they might look like. Of course, in real life, your data might look quite different, right? Your data might look like, let me see, let me just draw some picture of some data that's out here and there. And that data does not look Gaussian, because if I try to fit an ellipse to it, there's a gap in the middle where there's nothing going on. But I could try to fit two ellipses to this. So let me change the color to red and fit one ellipse like this and another ellipse like that, right? And so now what we've just seen, that we have managed to fit a couple of Gaussians to this data, right? And then, of course, real data will not look as neat as that. But it sort of gives a plausibility argument that, if you've got data that is spread around, even in high-dimensional space, I could sort of fit elliptical contours around sort of clusters of that data. And that's what corresponds to a mixture of Gaussians. So it is actually pretty much a universal approximant to distributions to have a mixture of Gaussian densities. And so let me define that next. So a random vector x its distribution can be modeled as a mixture of Gaussians if we can say that x, say, is distributed as Gaussian with some mean, say, m sub j, and some covariance c sub j with some probability pi sub j, and I could have j possible components of the mixture. And of course, these pi sub j's have to sum to 1. So that is the basic mixture Gaussian distribution. And of course, the density will look like an average of these densities. So basically, p of x in this case will be summation j equals 1 to j pi sub j times the Gaussian density with mean m sub j and covariance c sub j. So that's the mixture Gaussian density. How would we simulate mixture Gaussians? Well, we are going to use mixture Gaussian distributions for some of the artificial data that we use in our homeworks. So how do we simulate it? Well, we simulate it by saying, so let's see, simulation would be pick a component first. So, component j is picked with probability pi sub j. How do we do that? Well, that's, you basically generate a uniform random variable U is uniform over the interval, say 0 to 1, and then you just divide up this interval to get the probabilities. So let's see how we would divide up that interval to get the probabilities you want. So basically, there's a random number you have generated between 0 and 1, and if the number is between 0 and pi 1, then you would choose component 1. If the number is between pi 1 and pi 1 plus pi 2, you would choose component 2, and so on. And then you can see that since the pi's add up to 1, you would choose, I'm putting dots here so you can see, you would choose component capital J when the number is between pi 1 through pi j minus 1, which is this point, and 1, which is summation j equals 1 to capital J pi sub j. So basically, by dividing this interval between 0 and 1 appropriately and tossing this random number generator coin, basically, which gives you spits out a number between 0 and 1, you can choose a component. So once component J is chosen, if component J chosen, then generate a random vector from a Gaussian distribution with mean mj and covariance c sub j.